Thank you very much. So I will present today an agent-based model, as the title says, which is based on argumentation, a formal approach to argumentation. And this is a joint research, like Slobodan announced, between Christian and Annemarie. It's a really interdisciplinary group which we have ongoing here because Annemarie has a background in computer science, Christian is a logician and philosopher of science, and I come from philosophy of science. So we have a, and we also recently got an economist on board. So it's a fully interdisciplinary integrated research. All right, so let me give you a table of contents of my talk. So first of all, I will introduce the certain problems which exist in nowadays existing agent-based models of science, which motivate the idea that we should approach them somewhat differently. I will specifically focus on the problem of how we shall model scientific interaction, what scientific interaction means, and what are the challenges we face when we want to model something like scientific communication and interaction. From there on, I will move to our own framework, which is argumentation-based ABM. Agent stands short for agent-based model. And then I will show some preliminary results of our simulations. So, first of all, introduction. According to some authors of agent-based models, or formal models of scientific inquiry, the network structure of the 17th century science appeared superior to our own. Now, what these guys are claiming is that guys back working like this are better off than nowadays Google Scholar access and stuff we have nowadays. Now, this is puzzling to say the least. And if there are challenges like this posed in the literature, we have to approach them seriously and see whether these results hold, under which conditions they hold, and what they tell us about scientific methodology and scientific inquiry in general. So what are these agent-based models? What is their aim? Social aspects of scientific methodology and the problem of the division of cognitive labor are some of the topics which these agent-based models are designed to answer. So, for instance, how should scientists divide research tasks among each other in order to most efficiently achieve their goals? We have seen earlier today some agent-based models on this topic. Kevin Zollman has research on this stuff. Another question is how much should scientists interact and exchange information among each other? So these kind of questions are related to the social aspects of scientific inquiry, and we make these models in order to tackle them. And this is a list of some of the models existing on the market. Now, what is the advantage of these models? Well, they avoid hasty generalizations, which we get from the traditional case study approach. So if we look at what philosophers of science have traditionally been doing, especially in the field of integrated history and philosophy of science, we mainly see historical case studies, then you get some examples, and then you make conclusions which should hold for the general methodology. Nevertheless, the problem is that we can cherry-pick these historical case studies, and the question is, how are we sure that our results really hold? So the agent-based model approach avoids these problems, but it gets another set of problems, namely the problems which have to do with idealizations and simplifications, because of course we need to idealize if we are going to make these simulations with certain agents doing some stuff. We are necessarily going to idealize. That's why we need these models, because in a simple way they can give us some very important answers. But the problem appears when these idealizations do not really represent what's happening in scientific practice. And then we think we are modeling one thing, but actually we are modeling something entirely different. Then we tell scientists, you should do this and that. Here are our recommendations for science policy. But they tell us, wait a moment, what you're modeling is not what we are doing. And this is the kind of problem which we encounter if you want to say something important with these models. Now, what do these models tell us about scientific interaction? For instance, the question, what is the optimal structure of the information flow in scientific community? Or how should scientists interact so that the community acquires the knowledge in the most efficient way? So this is these are the questions which these models have been designed to tackle. The main idea here is that certain social structures are more likely to lead the scientific community to prematurely convert on the false hypothesis or to prematurely abandon a fruitful hypothesis. And these are typical errors in scientific research. So false positives and false negatives. And the idea here is that if scientists interact in certain ways, they're more likely to do these errors. All right? So the question which we want to answer with these models is what kind of structures help us to avoid these dangers, or maybe if not avoid, then lessen the dangers. Now, a number of recent agent-based models of the division of cognitive labor have claimed that under certain conditions, increased information flow among scientists is not necessarily epistemically beneficial. So it's not always good for scientists to communicate. Too much communication might turn out to be epistemically harmful. Kevin Zollman's models are most prominent in this field, but there have been others which have come up to similar results. And these conclusions, especially Kevin's conclusions, have been pretty influential. And when I say influential, I don't mean only influential in the literature on formal epistemology, but actually they have posed concerns for philosophers of science themselves. So, for instance, if you look at Brad Ray's book on social epistemology, inspired by Zollman's results, Ray argues that full communication within the community of scientists would be detrimental, for effective lines of community not only serve to spread the truth, they also serve to spread falsehoods. So Ray takes Kevin's conclusion and calls upon them making a conclusion for the actual scientific methodology and actually existing scientific practice. Similarly, if you look at the Stanford Encyclopedia entry on social epistemology, Goldman and Blanchard argue that Kevin's results are another illustration of the idea that prima facie detrimental features of practice of science, namely reduced communication and dogmatism, may in fact be epistemically beneficial. Now, why is this so challenging? Well, it poses a direct challenge to the literature on scientific diversity. So now we go to another camp of philosophy of science, namely traditional approaches, which are concerned with integrated history and philosophy of science. And these are mainly nowadays scientific pluralists. So, for instance, Helen Longino has argued that interaction is essential for the production of scientific knowledge. Similarly, if you look at work of Ha-Seok Chang, he also argues that we want scientists to critically exchange information as much as possible. And the main idea here is that one of the essential features of scientific objectivity is actually what has been dubbed by Heather Douglas as interactive objectivity. So unless scientists have critically exchanged information, they can't even gain knowledge. So here we have quite some different recommendations to scientists what they should do. On the one hand, agent-based models tell us under certain conditions you shouldn't interact too much. Pluralists tell us interact as much as possible, and the question is what should scientists do, or what should we as philosophers of science conclude on the basis of these results? So now, in this talk, we will argue that the notion of interaction, which has so far been employed in these models, is actually not really representing scientific interaction as it actually occurs in scientific practice. And we will explicate this notion of scientific interaction and show why these idealizations currently employed are actually making these models suboptimal in the sense that they are not really relevant for the current recommendations for what is happening in science. And then we will propose a different model which is able to capture this notion. All right, so first, how shall we model scientific interaction? If you think of scientific interaction, the questions which we need to answer are which kind of interaction, in the sense of exchange of information, is relevant for scientists and their decision making, and how do scientists respond to new information? So if you think of scientists exchanging their papers, they go to conferences, they discuss, then one of the key features which distinguishes scientific interaction is critical assessment of new information. So when you get new information, then first of all, you critically assess it, and then you can first of all accept it. Then the second option is that you can doubt this information. And then the third option is that you can reject it. You just find it plainly false. But before you accept it, you doubt it, or you reject it, as a scientist, you're supposed to do some critical work with it. So what happens is the following. You have two scientists, each of them working on a rivaling hypothesis. One publishes the paper, namely this guy, and says, I have a new evidence which confirms my hypothesis and shows that your one is wrong. Now the other guy says, this is one option, one scenario, is that the other guy says, okay, your counter evidence is really convincing, I've seriously done something wrong, I give up. But that's not the only scenario. The other possibility is that this other guy, or a girl, or a woman, reads this paper and says, wait a moment, your results are fishy. I don't necessarily agree. I don't really disagree, but I need to go back to the lab. I have to reconsider. I have some idea for how to proceed further, but I'm not giving up. This is a typical reaction of scientists. They are ready to go back to the lab, find new ways of proceeding further despite of the current problems and anomalies. And then we have a third option where the scientist says, wait a moment, you've done a mistake. Your evidence is bollocks. I don't buy it. So this is a rejection. I just don't go into it. So these are different scenarios which occur in science regularly. If you look how scientists argue with each other via papers, in the conferences, you have at least, these are three possible scenarios. They are not the only ones. But at least these three scenarios occur frequently. Now, in most agent-based models, we have a simple exchange of information. What happens is that agents receive information before critically assessing it. So they just gain this evidence, they take it in their bag of knowledge, and they accept it. Some models, such as those based on Hexelman and Krause, and models have tried to soften this idealization by introducing certain noise, or changing the degree to which scientists, agents in this case, trust each other. But none of this captures the argumentative aspect of scientific inquiry. Now, what does that mean? That means that when you receive new information, your scientific practice, the activities which you are going to perform, are going to change. Or may change, not necessarily. But let's say you receive an objection. Now, you're not going to perform one experiment, but you will perform maybe some other in order to reply to this objection. So this argumentative exchange between scientists can actually influence the way how we uncover errors in our research. And none of the models, up to our knowledge, of scientific inquiry is capturing this. So some of the key features of scientific interaction which we want to be captured by a model is that, first of all, scientific interaction is argumentative in nature. What does that mean? It means that the evidence is not just taken over, but it is interpreted, inferences are drawn from this evidence, and then we critically assess it, and then we form our views or beliefs or certain conclusions about our theories on the basis of this evidence. Second, criticism may help scientists to discover errors in their results. So when scientists exchange information, they don't necessarily just adopt it, but they may take this criticism to find what's wrong in their theories. So this criticism might actually be epistemically beneficial in removing these errors in research. So scientists, just imagine some scientists working on some hypothesis, and they're just overlooking this one really simple error, but they just overlooked it for ages. And now the other team reads their papers and they tell them, you've just overlooked it. And then the scientists will change their hypothesis or something else. But this kind of stuff happens. Historical examples are easy to find. We can come back to that in the discussion maybe. Third, different information is not only received differently, but it may trigger different activities on the side of the receiver. Now, if you look into the classical literature on methodology of science, Lakatos has a very nice representation, very nice cases on this topic, that when scientists receive objections, they look for something what he calls negative heuristics. So they look whether their research program is capable of finding ways for proceeding further and tackling these objections. So what Lakatos shows is that if your research program has a certain methodological apparatus for finding ways to tackle these anomalies, at least in a methodological way, so that you know how to proceed with finding solutions for these problems, then it's still worthy of pursuit. So what happens then is when scientists receive objections, they go, this is the example of going back to the lab and try to tackle these objections. So your research program has something methodological you fall back onto, and this is influencing your scientific activities. And finally, there are some other features. For instance, critical interaction is time costly. So if you read papers which criticizes your work or which belong to an alternative theory, you are not spending time doing your own research. So we have to include this time costliness into our models. Agents who interact a lot are going to do less time doing their research. So if you want to measure the success of our scientists in terms of time, it's important that we take this factor also into account. So this would be just a minimal set of features which we would like to argue has to be captured by agent-based models if they are to be relevant for the scientific practice. Okay, so now we go to our model which is able to do that. So I hope to be able to convince you of that. Here is the basic idea. In our model, an essential component of inquiry is argumentative dynamics between scientists. Our agents, who represent scientists, move along what we call an argumentative landscape. You will see in a moment what that is. And this argumentative landscape represents rivaling theories in a given domain. So we represent rivaling theories in some argumentative structure. We let agents walk along this landscape, exploring it, and we check under which conditions they can most efficiently discover the best theory, which is predefined as such. So we have different rivaling theories, but only one of these is defined as the best one, and we check under which conditions agents can discover this best theory. All this looks something like this. This is a nice drawing. So we represent theories as consisting of arguments which are taken in an abstract way. So each of these nodes, you can consider that to be an argument. These arguments are connected via what we call discovery relation. That means that an agent who starts from the root of this tree can walk to this argument only via certain paths. This is what we call discovery paths. And these different arguments, the arguments from one theory attack from arguments from the other theory and the other way around. So there are arguments, there is a discovery relation, and there is the attack relation. Now, these features we have borrowed from the field of abstract argumentation, which is a big topic in artificial intelligence. And the field of abstract argumentation is a broad research area, but the basic idea is it's really very simple. It comes from Doom's paper from 1995, and the idea is that you have arguments which are represented as just this abstract node. So each of these nodes is one argument. And what connects this argument is an attack relation. So errors represent attacks. So E attacks C, C attacks D, etc. Now, what we can look for in such a graph are certain rationality requirements. Just think of this representing a debate, and now we ask which stance how can we represent a stance of a rational agent in terms of which of these arguments? So, for instance, we don't want the agent to hold a stance which consists of two arguments which attack each other, because that would be a conflicting stance. An agent should have arguments which are mutually conflict-free. So first feature would be conflict-freeness of arguments. For instance, this D, the colors are awful here, so I hope you see, but the D here and E form a conflict-free set. And also, there is a notion of admissibility. So a set of arguments is admissible if it can defend itself. What does that mean? It means it attacks all its attackers. So C attacks D, but E attacks C in terms, so E defends D from C. So E and D are an admissible set of arguments. So we would say that a rational agent can hold E and D stance, and then we can have certain labelings. For instance, the green arguments, I don't know if you see, but E and D are green. They are accepted because they are fully defended. C is rejected because nothing defends C. And B and E and A, they attack each other, so we are undecided about this issue. So these are certain rationality requirements, a very elegant framework for capturing different kinds of debates. And a few years ago, Christian and I have used this framework to capture scientific debate. We have illustrated continental drift debate by using this framework and showing how different arguments in these debates were attacking each other. So the framework is, what we have argued in this paper is the framework is suitable for capturing scientific debates. But now in this framework we go agentive. So we add agents to our landscape. So this is how our model looks like. It doesn't look so cute like on the previous picture. This is actually a screenshot from .NET logo where it is programmed. And Anne-Marie is our key programmer, so she's the main designer of the program. Our model, like I mentioned, consists of an argumentative landscape which represents rivaling scientific theory. Now, each theory is represented as a tree which consists of conflict-free arguments which are connected by a discovery relation. What does this mean? So here we have two theories. This is one theory, this is another one. Each theory has discovery relations. These are these green lines, and these are different arguments. I will explain why I have different colors in a moment. But what I don't know if you can see, there are red lines between these two different theories. These are attacks. So arguments from one theory attack the arguments from another theory. Now, when our agents start from this graph, the graph is gray because agents don't know where what is. So only you see, this is from the God's eyes point of view, everything is gray, and agents, there are these two green dots, they are just on these first arguments. And they discover this landscape only gradually. Now, when we speak of arguments, what we mean by that is, what we would like to represent by that is hypothesis for which you discover evidence gradually. So you discover whether your hypothesis is corroborated or whether there are some problems because you encounter an attack. So an agent remains on a certain argument, works on this argument, and while she works on this argument, she discovers problems, namely attacks coming from other theories. She can also discover these problems via communication with other agents, but we will come to that in a moment. Okay, so what happens then is that over a certain time, the agents discover more and more, and they discover this all different colors. So they are discovering these discovery relations and attack relations. And we can represent also more complex structures. So we can represent this is, for instance, a graph with a landscape with three theories. This is one theory, here is another one, and here is a third one. And each of them has three levels of depth of arguments. We can come back to the specifics of how this is designed later, but they are all equal in the size. And then agents discover it, and the colors change. Now, how does this exploration look like? So, like I mentioned, scientists are represented as agents who move across the landscape and explore it. And they have three different ways of exploring this landscape. First of all, they can explore a single argument, gradually discovering possible discovery and attack relations. And these are these colors which each argument represents. So there are 6 different colors an argument can go through. And the more an agent stays on an argument, she reaches different colors and finds out more and more about these arguments in terms of different relations, discovery or attack relations. Then an agent can move to another neighboring argument, or she can move to an argument of another theory, because she makes a certain evaluation which tells her that another theory is better. I will come to that in a moment. By exploring this landscape, agents form their subjective knowledge. So they slowly learn more and more of these arguments, and this forms their subjective knowledge, which ideally would reach the whole graph. So they would ideally find out the whole objective graph if they learn about all theories. Now, our agents are also equipped with certain decision making. So every 5 rounds, they make an evaluation of all the theories in view of this subjective knowledge they have gained up to that moment, in view of the available information, and they, in view of this, decide whether to keep on exploring their current theory or whether to jump on another theory. Now, which criterion did they use? Well, namely this admissibility, or a weakened version of this criterion. The idea is that they always want to pursue the most defended theory. So they calculate which of the theories, in view of the knowledge they have discovered, is most attacked. And if their current theory falls under a certain threshold, they jump to the theory for which they know it is more defended. Now, this is a very broad framework, as you can imagine. But the initial version of our model is designed to investigate how different social networks, so in the sense of these different structures of communication, impact the efficiency of scientists in discovering the best of the pursued scientific theories. So we want to see how does the information exchange help agents or harm them, in discovering the best theory. So in this version of the model, our landscape consists of 2 or 3 theories. We have run simulations for both of these landscapes, and we have defined the best theory as fully defensible. This is an idealization, of course. No scientific theory is rid of all the problems. But in order to investigate under which conditions agents are successful, we have helped them out by defining the best theory as fully defensible, and then we look at under which conditions they can go on to work on that theory. Now, we also define the successful run of a simulation as the one in which, at the end of the run, the number of agents working on the best theory is not smaller than the number of any other theories. Now, this is a relatively weak notion of success because it's different from a convergence of agents, but actually in our simulations, agents most of the time just converge on one theory. So we would say that our agents are successful also if they haven't all converged on the best theory, and we are happy if they just haven't abandoned the theory, or actually if not less agents are working on the fewer number of agents are working on the best theory, but in most simulations they actually all of them just go on one of the theories. Our notion of social networks is different than the one used so far in the model. So in Kevin's and another Grimm's model, the notion of social networks is represented as a simple exchange of information among a certain number of agents in certain networks, in certain structures. Vlastek has shown this. There is this cycle, wheel, and complete graph. But we have approached this somewhat differently because we think that the situation in science is somewhat complex. So first of all, we allow our agents to form collaborative networks. These collaborative networks, we put 5 agents in each network. This is an arbitrary choice, but we thought of collaborative groups of 5. And in these groups, agents can start from the same theory, in which case we call this a homogeneous group, or they can be put on different theories. And then it's a heterogeneous group. Now, when they communicate within a collaborative network, they share all information. The idea here is, just like in every research group, they just share all information because they're doing a joint research. But the way how they exchange information with other groups is defined in terms of probability in our model. Now, what does that mean? It means that every 5 rounds of our simulation, an agent communicates or shares information with another agent from another group with a certain probability. So if a probability is 1, every 5 rounds, an agent will exchange information with a member of another group. The idea here is that the extent of information sharing is measured in terms of 2 different criteria. First is the frequency with which an agent communicates, and the second is the number of agents. So we thought that this is a more realistic representation of how communication works. It's not only that you talk with more scientists, it's also that you talk more frequently with other scientists. But at the same time, that will cost you more time, because every time you talk, you're wasting time from your own research. And we have also looked at another feature, namely we have modeled reliable and biased agents. So reliable agents are those which share all information which they have gathered in their direct neighborhood. So the idea here is that it's like writing a paper. You write a paper about your recent results. But biased agents, they only tell you nice stuff about their theory, but they will not share the attacks on their theory. So every time they learn that there is an attack on the argument on which they are working, they don't share this information. So they are biased in this sense. They don't share the negative stuff about their theory. So this is our model. Now, before I show you preliminary results, I would just like to show you how the net logo looks like. So this is the basic setup. We can here choose the number of theories, the depth. This indicates how deep the theory will go in terms of levels of arguments. And then we can set other parameters. And then when we started, I just have to move this up. As you can see, agents, here we have 3 theories with 10 agents. And the colors are awful, but they are blue guys jumping here. And they are moving along this landscape, and here you see how they are performing. The red line indicates the best theory, so this shows you the popularity of agents on each of the theories. In this case, everybody is converging on the best theory, so they are successful. So that's how our run looks like. Okay, I will just go back to the slides. Okay, let me show you our results. So these are just preliminary results, and I will comment on them at the end of the talk. First of all, we looked at how increased information sharing impacts the success of agents. We have found out that increased information sharing does not lower the success, but it reduces the time needed for agents to complete the run. So even though they waste time or spend time, invest time on sharing information, they are actually faster. So these are the plots which we have run. We have run 100 simulations for each number, for 10 agents, and then for how many? 20? And 100 agents. So you have here different groups. The red line here represents what happens when they don't share any information. As you can see, they are performing horribly because this is for homogeneous groups, so this is for collaborative groups where each starts on one theory, so they will not find out anything directly about other theories, so they are performing very bad. But these guys here, they are representing agents who share with the probability of 0, 3, 0, 5, and 1. And as you can see, these are very similar lines. The pink one are those who share the most. So they are performing quite fine. But we would, because of the possibilities of errors in some simulations, we can say that these are very similar results. But if you look at the time now which they need for this, here is the pink line. This indicates those who talk the most with each other. They are much faster than these guys. Now, of course, one could say that we have given them too less time for our modeling of how costly information sharing is too charitable, so that actually they don't invest much. I can give you now a short description of how much time they invest. So if you imagine that the scientist works 5 days a week, our agent who works 5 days a week spends every Friday on sharing information. That means that out of 5 days, our agent don't do the research on Fridays but talk. If the probability of the model is set to 1, that means that they will do this every Friday. If the probability is 0.5, that means that every Friday they will flip a coin and then they will share information. So you can think of that in those terms. Now, of course, if you think that sharing information costs more time, then this would have to be increased. But we found that this is quite a realistic setup. We can, each argument, for instance, would, in this, if you translate the model in these terms, then each argument which represents hypothesis would need 5 weeks to be discovered. So they need, every week they work 4 days a week, 1 day a week, they exchange information, and then after 5 weeks, they discover the whole hypothesis. That's the basic idea. Okay, now the results regarding reliable and biased agents. Reliable agents perform more successfully than the biased ones. So here are plots. The black one represents the biased agents. This is sorry, I didn't say. This is the number of successful runs, and this is the number of agents on the on this axis. So the red line represents the reliable agents, and these are the biased agents, and they are obviously less successful. This is for the probability of communicating one. So here is for reliable and biased agents if they talk a lot. But if they talk with the probability 0.5, the results are somewhat similar. So still the biased agents are worse off. But if you look at the time, these are the plots for time for these two plots for success, which I have just represented. They are quite similar. So it's not like they are faster. They are similarly fast, but they perform worse off. So the conclusion here would be that the reliable agents are performing better. Finally, we have looked at what happens with homogeneous and heterogeneous groups. Homogeneous are those which start on the same theory. Heterogeneous are those which form collaborative groups from different theories. And here results are as expected. Heterogeneous groups perform slightly, here stands heterogeneous groups perform slightly faster than the homogeneous ones. This is because heterogeneous groups start from different theories and they are able to find out information about best theory sooner. They are not though performing more successfully, or as you can see, here, homogeneous group is the red one. It's just slightly better off than the heterogeneous ones, but we wouldn't consider this a significant difference. And we can explain why later on, but for now, just take my word for it. But if you look at the time, so these are the heterogeneous ones, they are performing quite faster than the homogeneous networks. So this is the final result. Okay. One disclaimer regarding these results. We wouldn't be as fast as to claim that any of these results hold for the actual scientific practice. Our model is still, just like any other agent-based model of science, just a bookshelf model. And we have to be very cautious regarding these results not to think that this tells us something about scientific practice. Why? Because we would have to make sure that all our parameters are really relevant for the parameters in the actual world. So this is an important thing. Nevertheless, we think that our model is closer to scientific practice, so it's one step closer than the existing ones. And then we would like now to check for parameters and in which scenarios they would be adequate. So for instance, one thing which we would like to check is what is an optimal way to model the time spent on receiving information. I told you the story about Fridays. This is one way to interpret that. Another thing is maybe we should add the effects which competition has on scientists. So when they compete with other scientists, maybe they are faster. In which way, when they discover there is a rivaling group working on another theory, maybe they should speed up their research, stuff like that. Of course, these results would have to come from empirical studies in the real world. Another question which we would have to answer is whether our results are robust under minor parameter changes. So this is quite a challenge for our model because it's quite complex, but this is one of the things which we intend to do in future. And then another interesting question is which argumentation structures correspond to specific scientific domains. So in our model, we have represented scientific theories as being attacked 30%, in such a way that 30% of a theory is attacked by another theory. Now, maybe this corresponds to, let's say, theories in medicine, but maybe theories in physics or in sociology will look quite differently. In order to answer what is an adequate representation of this, we would again need some empirical findings, for instance, citation analysis, or the guys working in artificial intelligence are doing argument minings of scientific papers where they are trying to represent the argumentation structure in the certain scientific domains. So this would be useful. This would be useful information to represent argumentation structure in science, and then to see which of them would serve as landscapes in our models. Finally, just to mention the possible enhancements of our models. So, as you have seen, all our agents, I just showed how all of them behave, but they all behave in the same way. This is another idealization. So what we could do with the model is implement different heuristics or different behaviors of agents. One possibility is to introduce what Weisberg and Mullen have called mavericks and followers, so scientists who like to go there where nobody else has gone so far, or followers, they follow the crowd, so they go there where others are. Another possibility is that we could model agents who prioritize search for defense of their arguments, or those who prioritize discovery of new arguments. They don't care about defending, they just all the time want new results. These are relatively easy implementations. And then we can enhance the model with tools coming from the abstract argumentation. So for instance, there have been work on values and preferences added to arguments. Then we can add explanatory relation or a set of explananda in order to refine what the best theory is. So instead of just looking at how defended a theory is in terms of arguments, we could look at whether scientists have discovered certain number of explanations for a certain set of explananda. There are some preliminary ideas on that already, a preliminary model. And finally, one more enhancement which would be interesting is to add probabilistic argumentation semantics into our model. So this is something which has been done in the field of abstract argumentation, where probabilities are added to the, in terms of argument strength or the errors which attack, errors representing argumentative attacks, but which we haven't implemented yet. But that would make the model maybe even more interesting. So that's all. Thank you.